Today we're going to make a sheet metal part with the new CNC plasma table, and we're going to walk through the entire workflow from the CAD to the cam to cutting it out to folding it to shape. Stick around. Welcome back to Cloud 42. I'm James. Well, if you've been around the channel long, you have seen my CNC plasma table and you've seen my new electromagnetic sheet metal brake. And today we're going to use those tools and actually make a sheet metal part. Now, I've gotten a bunch of requests to talk about the software workflow for the Langmuir Systems Crossfire plasma table. And to be honest, the documentation that they provide on their website is not great. If you have just the basic table, then they have a series of videos that walk through all of the steps. But if you have any of the optional accessories like the Z-axis or the torch height control, then you have to ignore certain parts of the video and supplement with written documentation on the website, and you have to figure out how to put it all together. Now, I've done that, and I've got this working, and I've got the workflow sorted out, and we're going to walk through that today. And that process starts with designing the part that we want to make. The first part I'm going to make on the plasma table is not a surprise if you know me very well. It's an upgrade for the plasma table. And if you go out and look at the Langmuir forums, there's lots of references and lots of people have models for these torch shields. And the idea is the plasma torch is going to splash up water from the table and it's going to get onto the handle and in particular into the trigger switch. And so there are several designs out there for these sheet metal shields that just go on the two screws of the clamp to shield the torch from that water splash. Now, I started out by just trying to come in here and download one of these, and I didn't get very far. The one that I picked had a bad DXF file, at least it didn't import properly into my tools. So let's just skip all that and design one ourselves. So this is one that I designed in Fusion 360. Of course, you could use, any CAD program to do this, but Langmuir Systems provides a CAM post-processor for Fusion 360, so that's what we're going to use. And it wouldn't be any fun to just use one that I prepared earlier, so let's design one from scratch. Now we're going to design this part in the sheet metal workspace, so we'll just come over here and click sheet metal, and the first thing we need is a sketch. And I'm just going to put this sketch on the XY plane, and we will start with a rectangle. Pull this out, set that down. I'm going to hit D for dimension, and let's give our rectangle some dimensions. Say 6 1/4 inches long and 2 inches wide. Now, I'm working in inches. You don't have to work in inches. This works just fine if you have your document set up for metric. I have mine set up for inches because that's convenient for me. So go ahead and rage down in the comments about how inches are inferior. I know that. So we'll finish the sketch here and we will create what's called a base flange. So whenever you're working with sheet metal, the unit of work is the flange. So I'll select this area, come up here and click flange, and I have to select a sheet metal rule that I want to use. Now, we have an aluminum, that's aluminum millimeters, aluminum inches, default, and this is not for the thickness of aluminum I'm going to use. I'm going to use 050 aluminum, 50 thou, and again, you can do this in metric if you want. So I'll just accept the default, and then we'll come up here and click Modify Sheet Metal Rules, and we'll modify this rule for the sheet metal we're going to use. Click the pencil to edit it. And my sheet metal is not 080, it's 050. And you have the K factor here you can specify, which specifies how the material bends. 450-52 H32 aluminum 0.44 is a reasonable guess. You can calibrate this by actually bending your material, but I'm just going to use all the defaults in here because we're not trying to hit an outside dimension on square corners with this. I can leave that for later. So that gives us our sheet metal rule. And then now we can start pulling up the other flanges. So I will select this top edge here of the end, click flange, and I will pull up a flange. And I'll bring this up 0.6 inches. And now we have actually built a bend, and there are a bunch of parameters. If I go back in and look at this flange, you can control whether the bend position is inside, meaning that this outside face will line up with the end of the part that it was pulled off of. So you can see that that bend pulls up so that it is inside the part. You can set this to outside, or you can set it to adjacent so that the bend is all outside the end of the part. However you want. I generally use inside unless I have a reason to do otherwise. So pull that up 0.6 inches. And this is going to be the plate where we're going to screw it in. So I'm going to right click here and create a sketch. L for line, set that to construction, and we'll just pull a couple of construction lines across aligned with the midpoints. Create a point, and then mirror that point around this center line. Then hit D for dimension, and I will dimension those 2 points. I know these are 1.55 inches apart because I measured on the plasma table after I already made one 1.5 inches and it didn't fit. So that gives me my 2 points, and we can go back over to the solid workspace, select hole, pick both of those points, set my holes to, it's a 1/4 inch screw, so we'll make it 0.26 inches so there'll be a little bit of clearance. Okay, and that gives us our holes through that part. Go back over to sheet metal, and we need the wings that come up on the side, so I'll click this top edge here, click flange. We'll pull that up. We want that about 1.5 inches, but I don't want it at 90 degrees. Let's pull that out at 55 degrees. Okay. That looks good. And then we want one on the other side as well. So I'll select construct here, and I will say mid plane, and I'll just select a couple of planes that are on opposite sides of our part. That'll give us a mid plane that's right down the center. And then we will go back to the solid workspace here and select mirror. I want to actually mirror a feature, and the feature that I want to mirror is this flange, and the mirror plane will be the center. Okay, and so now we have a flange on each side. Now we're almost done. I want to go ahead and curve some of these corners. So hit F for fillet, and I will just select some of these corners. And let's see, 0.5 inches. That looks pretty good for that. Hit F again, and we'll fill these corners. 0.2 looks pretty good. And then I want to fillet this corner down here too. .50 thou looks pretty good. Now, if you take a look at these corners, you can see that Fusion has automatically added some relief here so that the bends don't collide and crease up in the corner. There's a bunch of settings in the sheet metal rule for exactly how that's handled, but we're going to ignore that for now. Let me turn off our construction, and this is the part ready to make. Of course, to actually make this part and cut it out, it's going to be flat. So let's go back to the sheet metal workspace, and let's click on Create Flat Pattern. So I'll click that. They want to know which face is stationary. Click here, click OK. And now we have a flat pattern of the part. And based on the K factor and the other parameters in the sheet metal rule, Fusion has automatically added bending allowances here, so we don't have to add extra material or think about that ourselves. If we cut this out and bend it, and if the K factor we provided in the sheet metal rule was correct, then the part will come out the right size. Now I can click up here and just say Finish Flat Pattern to close it and go back to the part. And then the flat pattern is over here in the tree, and I can activate it at any time just by selecting it. And now it's active. I can actually do work on the flat pattern, click Finish Flat Pattern, and it goes back to the 3D model. Now to actually cut this part out, we need to set up the G-code for it, and we do that over in the CAM workspace. I'm going to first activate the flat pattern because the cutting is all going to happen from the flat pattern. So I'll come up here where it says Design, and pull this down and instead select manufacture, and this will take me over to the manufacture workspace. And we've got the flat pattern open here, and we're going to use this to set up our cam. First thing we need is a setup, so I will click here to create a new setup, and I'm going to come over to operation type and set this to cutting. By default it's set to milling, which is what I often do, but we're going to be cutting here. And so the first thing I need to do is get the work coordinate system set up, and I'm going to click the body of the y-axis here and click a line on the left of the workspace, or on the workpiece. So it's going to align the y-axis in this direction. Then I click the head to flip it over to the other side. So this is the orientation I want. Now I'll click the origin and click this top lower left corner. So now we have our 0 point on the top of the sheet metal in the lower left corner with the Y oriented the direction that I actually want to cut this. Then for the model, I'm going to click body here, and I'm going to click on the flat pattern. So we're going to designate that this flat pattern is the model that we want to cut out. We're going to go over to stock and define what the material is we're going to cut out of. Relative size box is fine. Stock offset mode is set to add stocks to sides and top and bottom. So on the sides, I'm going to add 1/4 inch on all sides, and then the top and bottom, I'm going to add 0. So this is, as far as it's going to know, I'm going to have a piece of sheet metal I'm going to cut this out of that is 1/4 inch larger than the part on all sides. In reality, it'll be a much larger sheet, but that doesn't matter. And we can just click OK, and now we have our setup. So now we need to add a cutting operation. So I'll just click up here, cutting, which is a 2D profile. And the first thing I need is a tool. And if you don't have anything set up, I actually already have some plasma cutting tools defined, but we can go ahead and just add one. So if you don't already have one, you can come in here and just hit plus and choose the kind of tool. And we're going to create a plasma cutter tool. And we can give this a name. Standard consumables on the Hypertherm. And on cutter, the most important thing is the kerf width. And I know that my plasma cutter is about 50 thousandths. Kerf width with the standard consumables, you can, 0.55 is kind of pretty standard, but you can look this up for your plasma cutter, or you can experiment to determine what it is. And for the nozzle clearance diameter, I'm going to say that my nozzle is about 1 inch in diameter, and it ultimately just uses that if the nozzle is going to stay down and it needs to steer it around existing cutouts in case something tips up. Because we're going to use the torch height control, it really doesn't matter that much. You can define holders and other kinds of cutting data in here, but it really doesn't get used because the cutting feed rates are going to be defined in the program. And the output for the post-processor doesn't really matter because we only have the one tool with the plasma cutter. So we can just hit accept, and now we have our tool defined, and we can just select that and go back to the 2D profile that we're trying to set up. Now I'm going to set the cutting feed rate here to about 150 inches per minute. And I'll just go ahead and set the lead in, lead out, all of these to 150 inches a minute. This is dependent on your plasma cutter, the current, and the type of material and the thickness. I know because I've experimented that this material that I'm using, this 050 aluminum, cuts pretty well with the standard consumables on this 30 amp plasma cutter that I have at about 150 inches a minute. And this will definitely vary depending on your tools. So then we need to go in and select geometry, and we're just going to select the contours that we want to cut out. So we want to cut out this hole, and this hole, and the entire outside of the part. Now these arrows indicate where it's actually going to cut. So if for example, this arrow here is on the inside, if I click, it'll flip to the outside, and it'll actually try to cut around the outside of this. I actually do want it to cut around the inside. So this one's going to cut around the outside. These are going to cut around the inside. We can go in and look at the heights. The heights don't matter because the torch height control is managed by the post processor. The stuff here on the passes does matter. We want sideways compensation set to left. This is because of the swirl direction on most plasma cutters. Compensation is in computer, meaning that the computer is going to actually keep the kerf on the correct side of the line. And then over on linking, this is where we need to set our lead in and lead out and sweep angles. This has to do with where the pierce will occur and how the cutter moves into the cut. And the real issue here is just that these holes are small. If we just take the defaults, we'll be fine on the outside. But to make sure that we're piercing somewhere in the middle of this hole, we need to change a couple of these. Lead in radius, I'm going to set this to 0.06 inches, 60 degrees. I'm going to go change this to 90 degrees. And we need 0 lead in distance. And then we're going to set the pierce clearance to 75 thou. Now I played around with these. You can play with these to get it where you need it. But I played around with it, and this does a pretty good job of getting the pierce to occur inside the center of the hole in a place that's reasonable. If you don't have this set correctly, you might end up trying to pierce someplace outside the hole, or in this case where we're cutting inside, if it knows that the pierce is going to interfere with the rest of the work, it just won't generate a path in here, and you have to go back and play with it. Now I can see I've got a lead out here. I don't need that, so I'm going to double click on this to open it back up, and I am going to uncheck the lead out. And that makes sense. We'll pierce, we'll cut around the part, and then we'll pierce here and cut around the exterior. So let's simulate this. Come up here and click on simulate and click go, and we can see what the plasma cutter is going to do. And this looks entirely reasonable. Now that we have the tool path all planned out, we just need to generate the G-code. So I'll come up here to Post Process, click on this, and the first thing we need to do is select a post processor. Now, Langmuir Systems provides a post processor. If you come up here to their website and go to the Downloads page, under post processors, they have versions, depending on which version of the table that you have, they have different post processors. And here's the one that I'm going to use, which is the Fusion 360 Post version 1.6. You just click here and it will download it. I already downloaded it. And then you go back into Fusion, and here where it says Post, we'll go ahead, click the 3 dots, and we will click Import, and go to the downloads and select the file that I just downloaded, which is this Fire Control 1.6 CPS. Now, I actually already have it in here because I already imported it. And when you import it, you can import it locally on your machine. I went ahead and imported it to the cloud so that it'll be available on every system where I start Fusion. And so I will just click Select, and it will select that post. Then I need to select an output folder for where that file is going to go. And I will just select a location. And then there's an option down here, Open NC File in Editor. I like to do that so that I can see the file that it's generating. And then here's where we set up the height information for how the cutter is actually going to behave. Now, with the particular torch that I have and the particular CNC shield that I have, I know that I want the cut height to be 35 thou, and we're going to count for maybe 10 thou of springback. This is when the torch goes down and probes and finds the work height. This is how much we expect the metal is going to spring back when the torch comes off of it. So this is just to correct for errors due to the metal flexing when we probe it. IHS is the initial height sensor. I have that, so I'm going to leave that checked. Pierce delay, we're going to go with 0.6 inches. And again, I just determined this by playing around with this material. Pierce height is going to be set to 125 thousandths, and then retract height is 1 inch. So it's going to cut at a height of 35 thou. It's going to pierce from 125 thou, and then at the end of the cut, it's going to retract up to 1 inch to clear the workpiece, and that's for moving around to avoid tip ups as we move the torch to the next cut. And we have the box checked for the torch height control because I have that option on this plasma table. So then we can just click Post, and it will generate the G-code. and it's already generated it. And here it is loaded up in Visual Studio Code. If you don't have this, it'll prompt you to install it, or you can just say you don't want to preview it and not even worry about it. Now, there's a bunch of mysterious stuff in here, and I didn't understand what it all meant, so I took the time to look it all up, and I have another version of this file that I've already annotated. And so let's walk through what kind of Gcode it's generating and what it does. The first part of the code here is just a preamble to set up the defaults so that the interpreter is ready for the Gcode that's coming. So G90 puts it in absolute mode, meaning all the coordinates will be absolute offset from the 0, 0 position. And G94 tells it that all feeds are going to be per minute. So if I say feed 150, it's going to be 150 units per minute. G17 selects the XY plane for cutting, and G20 sets it to imperial inch coordinates. This would be different if you're doing metric. H0 turns off the torch height control, and that's because we're just trying to zero everything out. We are not cutting yet. We're just going to switch that off to make sure it's not confused. So this gets the plasma table into a known state. And the first block here is to cut out the first hole. So G0 is a rapid. It's going to move rapidly to the X and Y coordinates of where it's going to start the first hole. G92 resets axes, so it's going to reset Z to 0. So at whatever height it happens to be, it's going to forget what it thought the Z coordinate is. It's just going to set it to 0. Then the next two are a two-part probe. G38.2 is going to probe until the torch height control switch makes contact. So Z minus 5 means it's going to go down 5 inches at a feed rate of 100 inches per minute until it contacts the workpiece. So it's trying to find the 0 height of the sheet of metal that's in the table. Now that's because it's moving pretty rapidly, that's not going to be very accurate. So then it's going to do a G38.4, which is going to probe until the switch loses contact in an upward direction, half an inch, at only 20 inches per minute. So it's going to go down rapidly till it makes contact, then it's going to go up slowly until it loses contact. So at that point, the torch should be touching the workpiece. So it resets Z to 0 again, then it moves up 30 thou. Now this is a combination of the spring back that we actually put into the post, plus the backlash that they know would be in that Z-axis, or that they're estimating in the Z-axis, just based on the design of the Z-axis. And so they're moving this up, so they've taken out that spring back and backlash and reset Z to 0 again. So at this point, this should be an accurate probed height so that the torch is sitting right on the surface of the workpiece. Now we're ready to cut, so it's going to move up to our pierce height. It's going to switch the torch on, and it's going to dwell. So it's going to pause for 0.6 seconds. That's the dwell, that's the pierce time that we put into the post. So it's waiting for the plasma jet to cut through the metal. Then it's going to rapid down to the cutting height, turn on the torch height control. So it's going to start monitoring the voltage and maintaining whatever height it's at right now, which should be the 35 thou cut height we programmed. And then it's going to start making the moves to actually cut out the hole. So G1 is a move, and then G3 is an arc, and it's going to actually cut out the hole. Then switch off the torch height control, switch off the torch, and then raise the torch up to the Z retract height, up to 1 inch. And then it's going to repeat. So for the next hole, it's going to move to the location. It's going to do the whole probing sequence, cut it out, turn off the torch. Then for the outside perimeter, it'll do the same thing. Move to the start position, probe it, pierce, go to the height, turn the torch height control on, cut all the way around the perimeter, and then turn off the torch, raise the torch to 1 inch, and then that's the end of the program. So the stuff's pretty straightforward, and it is actually a pretty simple post-processor because there's very little it has to do. It just has to probe, set the heights, and actually move the torch around to cut. So I think that's it for the software. Let's go out to the plasma table and run the program and cut something out. Okay, the first step is to load the Gcode file that we just made here into Fire Control, and I will just click the upload button, and we will choose, here it is, 1001NC, and it will load it into Fire Control, and we can see here it's generating a visualization. And this is exactly what we expect. So we can see the 0 point in the lower left corner and the path up to cut the 2 circles, and then the path around the outside. And so now we just need to set the 0 point where it's going to run. So I'll use page up and page down to move the Z-axis, get it down close here, and then just drive this around with the arrow keys and try to get close to where I want to be. So that's about the lower left corner, and there's plenty of material there, so we'll reach up here and hit 0 all axes. And we can do a dry run of the program. I'm going to go ahead and raise the torch up. I'm going to zero this up higher, so hit 0 all axes again. The Z height doesn't really matter because it's going to probe and figure that out, but we can enable the dry run switch and then just hit start, and it will trace out in the X and Y where it's going to make the cut. So hit start. There's the 2 holes. And the perimeter. And that looks fine. Program complete. So I think we are ready to cut. Make sure I have everything switched on. And I do. Plasma cutter's happy. It has air pressure. So I'll turn off the dry run. Put on my eye protection. And just hit start. And that is the part. I'm just going to dry off some of this water that's splashed up. Now this has got some dross on it from the process, and we'll take that off. Grab my non-tinted safety glasses, and I've just got a little battery-powered right-angle die grinder. This has got a roll-lock, 2-inch roll-lock disc on it with a Scotch-Brite wheel, and we'll just use that to clean up the dross. Okay, that's nice and smooth and clean, and take this over to the sheet metal brake and bend it into place. And oh, by the way, if you were confused by the fact that there appears to already be a torch cover here on my torch, well, this isn't my first rodeo. Okay, we've got the part all cleaned up and deburred. Let's just bend it. Just slide it in here underneath the magnetic clamping arm, and this one I'll just align here by eye. Looks about right. Let's try turning it on. And bend this up just past 90 so it'll spring back. That looks about right to me. Yeah, it's like about 90 degrees. So that's the screw flange. And then we need to bend up the wings on the sides. And I'll do this under the front, and I've got a little piece of the same material that I'm going to put under the back of the clamping bar as packing. And then I have very lightly scribed a little line here where I want the bend. Clamp that down. And I'm going to bring this up. We wanted 50 degrees, so I'll bring it up probably a little bit too far. See how that goes. That looks pretty good. And we'll do the other side. And that is the part complete. The combination of a CNC plasma table and a bending brake is a really powerful one for just quickly banging out sheet metal parts. Now, if you add a spot welder to the mix, then you've really got something special, but that's a different video for a different day. That's all I've got for you today. Thank you for watching.